In this video, we're going to start looking at doing actual reactions on alkynes. We saw some reactions where we, deprotonated a external alkyne, but now we're going to actually do some reactions to them, similar to things we've seen in Chapter 8. So starting off, we're going to do these hydrogenation reactions, very similar to what we've seen already again in Chapter 8. And in particular, these hydrogenation reactions are essentially adding hydrogen across the alkyne to make either alkenes, E or Z, right, cis or trans, or go fully all the way back to sp3 carbons with alkanes. And we also, this will kind of be true depending on what we're doing, we do not need to know the mechanisms, right, because they're kind of complicated and sort of inorganic chemistry related with a single electron transfer, so it's all sort of complicated. So for the first example, let's look at this reaction here, this palladium metal catalyzed reduction here, known as a full reduction. And as the name implies, we are fully reducing down the alkyne to an alkane. And one thing we need to sort of recognize is how many carbons are attached to the alkyne. So let's quickly number this. So there are 7 carbons on this molecule, right, on this hept3-ine. So when we fully reduce it, we come out to the following molecule, right, just heptane, right, like this. So the alkyne is fully reduced to an alkane. And so now for this other example here on the left, this sodium ammonia complex is known as a dissolving metal reduction with sodium. And sodium is really potent for these sort of reactions. It's pretty reactive itself. And so when we react this, the outcome is actually the E alkene, right, or trans. So it'll end up looking like this, where we have the alkene in the middle here, right, with those two groups opposite to each other, right, E. For the last reaction here, Lindlar's catalyst, shown right here, we get the sort of opposite situation, where instead of getting a E alkene, we get a Z alkene, right, or cis. So that ends up looking as such. Right, just like that. And so for Lindlar's catalyst specifically, you don't need to know the structure of it, but it is sort of this complicated palladium situation here with this quinoline group as shown down below. We don't need to know this or the mechanism, but it's a sort of a complicated sort of witch's brew happening here in terms of what's going on. So these are our 3 reactions here for hydrogenations, right? We can make an alkane, the Z alkene, or the E alkene. For the next reaction here, it's kind of the opposite of what we saw with making an alkyne using those elimination reactions. So we can add a hydrogen halide, right? Just like we saw at the beginning of Chapter 8 when we added a hydrogen halide across an alkene. And so we get this, right, just like we saw back then, Markovnikov addition, right, making the most stable carbocation. And when we do this, right, because when we react to an alkyne, we get to the alkene, we get a mixture of E and Z, so don't worry specifically about getting one versus the other. So let's go ahead and look at what we get here, right? When we add one equivalent of HBr, right, one hydrogen halide, we end up getting the, right, just the simple alkene. Right, like this. With that bromine, right, adding onto the more, right, stable carbocation. And then we get a full reaction to the alkane, if we add two equivalents, which ends up looking like this. And so looking at the mechanism for this, it is as follows, where again is very similar to what we've seen already back in chapter 8, where this alkyne is going to act as our base here, and it's going to grab a proton right from the HBr, our hydrogen halide, and our intermediate looks like this. We have a positive charge now on that carbon right there, and that hydrogen that was grabbed ends up right here. And in that second step, that Br minus will end up adding to our carbocation to get to our intermediate. Right, so with one equivalent of HBr, we will end up getting just this alkene, right? But if we add another equivalent of HBr, we do this mechanism again. So I'll leave this up to you to do, okay? This is just like what we did in chapter 8. Again, just to sort of point out the Markovnikov addition happening here, this carbocation is more stable, right, because it's right next to this benzene ring, right, this aromatic ring, which can do a lot of resonance with this carbocation, right? It's more stable right here. So I'll leave it up to you to do the mechanism for this next part, and we'll probably do one in class as well. All right, so for this last reaction we're looking at, again, a similar reaction to chapter 8, this oxymercuration reduction is this Markovnikov addition of an alcohol. Okay, and for this, we don't need to know the mechanism, right? Just like with that Markovnikov addition of OH back in chapter 8, it's kind of complicated, right? Mercury makes things kind of weird, so you don't need to know the mechanism, but we will need to know what's happening at the end here, right? You're seeing this, where we're getting this Markovnikov addition, where the OH is adding to the more stable carbon, right? And this alkyne is going to the alkene, and we're seeing this last step happening here, where we're getting something called tautomerization, right? We're going from this enol, right, an alkene alcohol in enol, and we're tautomerizing to a ketone. And tautomerization is kind of a fancy term for a rearrangement happening. And why is this taking place, right? You notice the brackets here. This means that this is purely an intermediate. It won't stop here for the most part, and most of the product, the major product, will end up being this ketone, right, on the more substituted carbon. And this happens primarily because external alkenes aren't very stable. Right, so our ketone here is a more stable product. All right, so let's look at a mechanism for how this is happening. So this is a mechanism, we will need to know, which of course is why I'm doing it. And so one way this can transpire is through an acid-catalyzed tautomerization, meaning, right, there's an acid involved, typically right, from H2SO4 or even water at the beginning here. So we'll sort of just paraphrase an acid as H+. Okay? And so the alkene here will end up grabbing a proton, right, and we get this, right, the carbocation will be on the more stable carbon, of course. And so for the next step, the OH, right, will want to donate its electrons down like this. To get to sort of our precursor here to the carbonyl, right, to our ketone. And in a final step, we can go ahead and say that H2O or some other base comes along and grabs that proton, right, to get to our final product here, right, our ketone. Okay. There's another way we can look at this as well, where instead of having an acid catalyzed rearrangement, we can do a base catalyzed rearrangement, which is what the next page here is all about. Right, so we have our enol again, like so. And instead of having an acid come along, we have a base. Right, so let's say it's O minus, or whatever base we might be using, is going to come along here and grab that proton. And so we end up with O minus here. And so for the following step, we see these electrons come down, and then the alkene here will grab a proton from somewhere. So we can use H plus or water, for instance, to get to our more stable ketone. Okay, and in truth, this won't really be relevant in class. I'm using these straight arrows here, right, to say, okay, this is happening 100%. In truth, these are actually in equilibrium, but for the most part, right, this ketone is much more stable. So the major product, the majority of the time, will be this ketone here, okay? So this is a situation where I'm asking for, okay, what's the major product of this reaction, right? And we're seeing these conditions here. We have an alkyne, right? I'm giving you water, sulfuric acid, mercury sulfate. You know that the final product is going to be this ketone on the more substituted carbon.